Hello. Okay, in this video, I want to talk a little bit about mass and the way it's defined and what we can do with that definition and some of the ways that the definition isn't complete or is circular. So first, there's this little thought experiment. Let's say that I have a turtle and I take the turtle to an icy pond, and I put boots on the turtle so that the turtle's feet aren't cold. Um, but then I give it a push. So the icy pond is there to prevent friction from being a factor. I'm just kind of pushing the turtle, and it moves based upon the way I'm pushing it. Um, there's a couple things to clarify here. First is what a push means. So for us, a push is a force. So we'll talk about it that way. So a push here is a force. Oops. A push is a force. And that's our technical term. And what we mean by a force is really anything that causes acceleration. So if you apply a force and it is something that might cause an object to accelerate if it was acting by itself, then that's what a force is. So I guess we can write it that way. So force, and a force is something that's proportional to acceleration for an object. So if I were, an important caveat here is if a single force is the only force acting on an object, then it will be proportional to the acceleration acting on the object. If there are multiple forces acting on an object, you have to keep track of all the forces acting on an object and worry about the net force on an object. We'll return to that in a little bit, but I want to keep it kind of simple for right now. So in this expression, you may or may not be familiar with this symbol. This means proportional to. It's an alpha. So all this means is that the vector force is proportional to the vector acceleration, assuming that that force is the only force acting on an object, which we're going to do right now. When you apply force, you cause acceleration, and you cause acceleration in the same direction as your force. So a question we could ask though is, well, how much acceleration do you get if you apply a force? And to answer that, I'm going to consider a slightly different case or an additional case. So let's say I have the same icy pond, and I take another turtle out there too. So let me take another turtle. I'm gonna put my other turtle down here, and it's a slightly different turtle. Maybe it's a bigger turtle. A bigger turtle, same density as the other turtle. It's still a turtle. It's got whatever density turtles have. And I take this bigger turtle and I put it on the ice too, and I give it a push. And my push is the same in both cases. So I apply a force in that direction. Let me name the turtles too. So this turtle on top, this is Shelly. And on the bottom, it's Bobcat. So the little turtle is named Shelly and the big turtle is named Bobcat. So a question I can ask is, what happens here? If I apply the same force to both turtles, which one's going to accelerate more? The intuitive answer is that Shelly's going to accelerate more because she's littler, and Bobcat is going to accelerate less because she's bigger. And what we mean by littler or bigger here is really we're talking about the mass. If something's more massive, it's harder to accelerate. So we would say that Bobcat's got more mass. So Bobcat has more mass and will accelerate less. That's just the intuitive way to understand bigness in this context. What we mean by mass is resistance to force. So you apply the same force to both turtles. The more massive turtle accelerates less. So we can define mass through that relationship. So mass is really a ratio of how much acceleration do I get out compared with how much force I put in. So if I think about what mass would mean, I can define mass this way. So if I apply a certain force, if I have more mass, I accelerate less. And if I have less mass, I accelerate more. So there's this relationship between force, mass, and acceleration. If I apply some amount of force, if my acceleration is high, it means that I'm dividing the force by a big number and my mass is small. So high acceleration corresponds with small mass. And if my acceleration is low when I apply that same force, then I'm dividing my force by something small and I get a big mass. So large mass corresponds with small acceleration and vice versa. And I can define mass in this way as this ratio of force to acceleration, assuming again that I'm just applying a single force here and keeping the case simple like that. You know, this is kind of a definition for mass. It's a definition for mass. You could define mass in other ways. And we'll call this inertial mass. And what inertial means there? Inertia means resistance to motion. So an object with a lot of resistance to motion has a large mass. And that's the meaning of inertia and why we would call this inertial mass. We'll see later a couple different ways to think about mass that are equivalent, as it turns out, but defined differently. Okay, this looks familiar. We could rewrite this another way, right? So we could rewrite this as F equals ma. That looks familiar. That looks like Newton's second law, almost. Arguably the most famous equation, period. Really useful, but it's coming from this definition of mass. And so one thing that's important here is to note that this equation or this law isn't really empirical. It's a set of definitions for force and for mass. And it's sort of a circular definition. And I want to talk about what that means. So let me take Bobcat and Shelley again. So I'm going to see if I can move Shelley and Bobcat down a little bit so we can deal with them on their own. Let me see if I can figure out how to do that. So Shelley, you come down here. So Shelley goes here. And we're going to bring Bobcat down too. And consider these cases together. So there are some consequences to this definition that are interesting and maybe a little bit unexpected. So what happens if I apply the same force to both of these turtles? If I wanted to measure the mass of Shelley, let's say. So what if I want to measure Shelley's mass? So, okay, so this equation up here suggests that what I need to do is I need to apply a force, measure an acceleration, and then take the ratio to calculate the mass. So what I want to do is I want to measure acceleration. So if I want Shelley's mass, or I guess I should say to get Shelley's mass, I need to measure acceleration and I need to measure force. Okay, so let's think about that. So is it possible to measure acceleration here? Probably. I'm applying a force. I could bring a stopwatch to the lake, the frozen lake. I could bring, a tape measure to the frozen lake, and I can measure how long it takes Shelley to go a certain distance and calculate acceleration that way kinematically. That's the kind of stuff we've been doing so far, and that seems okay. So that's fine. We'll put a little check mark there. We can measure acceleration. Wait, that says measure accelerate. Measure acceleration. All right. So what about measuring force? So how do we measure force? Well, okay, that's simple too. I can just use this equation, right? Because if I want to know how much force I'm applying, I just need to know the acceleration, which we know how to measure, and also Shelley's mass. But that's a problem because we don't know Shelley's mass. In fact, that's the thing we're trying to use force to calculate. So that is sort of an issue. We don't know how to measure force. We don't even know what units force would be measured in. And that's a little bit tricky. So let me propose a different way to think about Shelley's mass. So let's compare the way that Shelley responds to the force to the way that Bobcat responds to the force. So let's say that I measure Shelley's acceleration, and I get that Shelley's acceleration is something, let's call it A sub S. And then Bobcat's acceleration, when I measure that, is going to be A sub B. Before we do anything, we can assume that Bobcat's acceleration is less than Shelley's acceleration. That's part of the way that we thought through what a definition for mass could be. And so let's compare this quantitatively a little bit. What we do know is if we take this expression, F equals ma here, that's saying that if I apply a force, that's going to be equal to the mass of the turtle times the acceleration of the turtle. And that's going to be the same thing for both turtles because I'm applying the same force to both turtles in my example. Then what I know is that the force is equal to the mass of Shelley, whatever it is, times Shelley acceleration, but it's also equal to the mass of Bobcat times Bobcat's acceleration. And I can get a little relationship between the masses this way. So the accelerations are things that I can in principle measure. And if I wanted to know Shelley's mass, let's say, then that's the same thing as Bobcat's mass times this ratio of the accelerations, just by reorganizing that equation. And so let's take an example. So let's say that I measured Shelley's acceleration to be 4 meters per second squared, let's say, and I measured Bobcat's acceleration to be 2 meters per second squared. And that checks out, or at least that is okay because the Bobcat's acceleration is less than Shelley's. And we know that's going to be the case because Bobcat's more massive than Shelley. So if we just kind of plug that in, Shelley's mass is going to be Bobcat's mass times a half. So whatever Bobcat's mass is, Shelley has half the mass of that. And this is, at this point, this is the best we can do. There's no way to get absolute mass here. No way to get absolute mass. Or to get mass absolutely. But we can get it relatively. So no way to get mass absolutely, but we can get relative mass. Great. So that's useful, I guess, in a way. But what if we want to get absolute mass? I mean, we go through the world and we hear that things have certain masses. Things, the units we typically use are grams and kilograms. Those are units of mass. So the trick here really is just to pick something. If I wanted to say mass absolutely, I just have to define something to be 1 unit of mass. So how would that work? So let me go to the next page. Well, let me copy all this and we'll go to the next page. So, all right, if I copy all that, all right, so back to the problem. We can't get mass absolutely unless we pick something. So let's choose. Let's say that Bobcat is 2 turtles of mass. So I've just chosen a unit. I've said that Bobcat is 2 turtles of mass. Okay, just by definition, I've said that. I've established that as my unit. Now Bobcat is my reference, and he's 2 turtles. Or she's 2 turtles, I think. So if we know that, or if we take that as a given, then we can find Shelley's mass. because Bobcat's mass is now 2 turtles, and Shelly's is 1/2 of that. So Shelly's mass is just 1 turtle. So Shelly is a unit turtle. Bobcat is 2 turtles. And now I am talking about mass absolutely. And I can talk about the effect of force more directly. Why is that? Because if I know that F equals ma, then what I've got is, if I think about the force that's acting on Shelly, for example, so the force that's acting on Shelly is equal to her mass, which is 1 turtle, times her acceleration, which was 4 meters per second squared. So the force that was acting on Shelly is 4 turtle meters per second squared. That's how much force is acting. So by choosing a unit of mass, I've also become able to talk about force absolutely as well. But I can't define force or the units of force without the units of mass. So that choice of a unit for mass now determines the way that I measure force too, because this is a circular definition. As soon as I pick something for a unit for mass, I get units of force and I can quantify everything absolutely. I could have gone the other way too and just defined the force that I had. And if I define the force that I have as some value in some system of units, then that determines the units of mass that I end up with. The way that we do it in the real world is we've defined kilograms to be something. For a long time, kilograms meant there was just like a piece of metal in a basement in Paris, and that was a kilogram. They've recently changed that, which is kind of interesting. But for a long time, there was just a reference mass, and that's what a kilogram meant. And from that, we get our typical units of mass. So in the real world, we work with kilograms. We use kilograms or grams. Kilograms is the typical SI unit. And then we've defined that to be something we just picked. And then for force, the units we use are newtons. So kilograms for mass. For force, we use newtons. But a newton is not an independent unit. 1 newton of force is equal to 1 kilogram of mass times 1 meter per second squared. And the way to think about that is it takes 1 newton of force to accelerate 1 kilogram of mass by 1 meter per second squared. That's the choice that we've made. And so we have the system of units based on the choice that was made to establish kilogram as a unit of mass. So that's kind of interesting. And if you think about it, really all units are like this. Like we just said that we could measure acceleration, right? But there's units in that too. The units are meters and seconds. And somewhere along the line, someone decided what a meter was and someone decided what a second was. But in that system of units, we can now establish acceleration. And there's no independent unit of acceleration. We have distance units and time units. And now we have mass units. Those are sort of fundamental units of the SI system. So I hope this helped you think through some of the consequences of our definition of mass, and also Newton's second law, which we'll return to. And I'll see you soon. Okay, bye.